All right, welcome everyone. My name is Nagy. I am excited to give the first keynote of this AMLIES 2023 workshop. Thank you, Harry and Jan, for the invitation. After 2020, I'm excited to be back. This time I want to talk about designing grid interactive smart communities, especially using our tool CityLearn, which I will talk about, but also any other tool and what kind of pitfalls we have to think about and what are the opportunities that we can achieve. So let's jump right in. I want to give you a little bit of a background, why we're doing what we're doing, why it matters, and then I'll get into what is CityLearn and why did we developed it, and then I'll show you some results, and then at the end we'll talk a little bit about interesting directions or new things that could be done. So, like I said, I'm a faculty at the University of Texas. My group, works in a lot of areas. We focus a lot on things like human responsive infrastructure, occupant-centric control, intelligent infrastructure, automated, control of buildings, autonomous buildings, things like that, and everything that works around it. We're in an engineering department, so it tends to be a little bit more applied than pure computer science. But that's why we're closer to the applications. So why we're doing what we're doing: buildings use a lot of electricity, a lot of energy, usually for heating and cooling, or most of it is done for heating and cooling. And with that, buildings are directly contributing to climate change because a lot of that energy is generated using fossil fuels. At the same time, climate change is making things worse in terms of increasing average temperatures, which leads to higher cooling loads. It also leads to more extreme weather, which can be higher heating loads as well. So everything kind of comes back to some extent to haunt buildings while they're also actively contributing it. So it's a positive feedback loop to some sense. So the good news is we know what we need to do, which is we need to decarbonize the grid, which is what you see here on the left-hand side as a simulation, increase more and more the share of solar and wind. And at the same time, we need to electrify the grid so that the energy that we do use is not generated, or electricity that we do use is not generated using fossil fuels. And so that's the idea. However, as you're familiar with this concept, if you just increase the share of renewables, you'll end up with overgeneration at times when you don't need it or when you have enough, and you will have not enough when you need it, just because you cannot control the availability. So you could address this with overbuilding capacity extremely. That might be one way to do it, or move to places where it's available, which is another different approach. However, what I want to talk about is more about the flexibility that you need in your demand side. So in our case, in buildings, in order to move the demand to when you have supply. So this kind of energy flexibility is a theme of a lot of work, including ours. So I'm excited to show some of the results. One of the things that I'm, sometimes a little bit different, I feel, in other works is that I'm a lot more interested into more individual residences, single family homes, because there's a lot of them, like almost 70%, so not almost, but 70% of residential buildings in the US are single family homes. And so that means this is a really, really big potential to move that flexibility needle, but it's very, very hard in some sense because there's so many individualities. So in many ways, this is why you see a lot of these demand response studies done on, large electricity consumers, because they have the ability to move a lot of current and a lot of demand at once. However, here the idea is that you have many demand or consumers that can individually might be a little bit, but aggregated it can add up to quite a bit. And so how we can unlock this energy flexibility is kind of like a big driver behind our work. Now, this is obviously not something terribly new as a concept. The concept or the notion of interactive communities has been introduced a few years back. Here's the DOE's report on that. So as the DOE walks through this, it presents it with certain charts. One is these grid interactive communities can reduce the loads simply by being more efficient, in which case you have the same net load profile. However, you will, but you use a little less energy at the same time. So the overall shape doesn't change. It's just a little less during the day. So that's not good enough for what we're interested in. The next thing you can do in homes, in buildings in general, but in homes in particular, generate your own electricity. This is normally, reserved for solar, rooftop solar, etc. In which case you'll get your own personal duck curve if you have, sun during that day, or well sunlit roof. And so again, during the day, you will have enough, but in the afternoon, you won't. And especially when the sun goes away, a lot of the buildings that rely on the solar, again, will generate this large ramping, which in some ways is even worse because now you need to fire up the peaker plants for this particular peak or ramp. No, so that's still not enough, like I said. And so what we really want is the ability to move loads throughout the day, shed or shift, on top of being obviously more efficient and generate. But generally, what we're interested in is to have a more constant load profile where it's a lot more predictable. Maybe you don't export to the grid. You can see here, you don't go into the negative necessarily, but you have enough for yourself. And also you don't have these high peaks, you don't have the high ramping. And so it's a lot more homogeneous. And so this is kind of like the goal. This is where we want to go, right? So the question is how we get there. And one of the big drivers behind this is to also remember, or one of the big challenges, not drivers, one of the big challenges to remember, if you want to do this in homes, every home is different. It's rather challenging to, get there very simply, to do the same thing in every home. And so the solutions we come up with to do this need to be kind of like adaptive or adaptable to individual homes. And the way we can get there, of course, this is also not something terribly, it's not a secret. We need the ability to store and release energy throughout the day, or electricity in this case. And in order to do that, we'll need some sort of storage and we need some sort of control system. So that's kind of like what we're talking about today, not necessarily storage. We will assume electric batteries that we have. We have done, a lot of work has been done using domestic hot water heaters to do sort of demand response, or any other sort of thermal storage, chilled water, ice storage, things like that. For today, we'll be focusing on electric batteries, which are similar to EVs in a lot of sense. So that's kind of like the focus of our talk. And then the other thing is controls. And that's the larger part. So when we're talking controls for buildings, there's really three options you have. One, the classic rule-based control, and we'll call that RBC as we move forward, which is a set of, if then else rules. And so if something happens, then do something. Very straightforward, easy to implement, but it's not, optimal in any sense. It's also not easy to replicate, and so on. Then the next best thing that a lot of work has been done over MPC. This is an optimal approach, provided that provided you have a model of your plant or your building or the system you're trying to study or control. And even if you have disturbance model, you can also integrate those. And so then using your measurements at your whatever your time step is, you can integrate forecasts and then optimize your systems for an optimal trajectory over the certain time horizon, and then implement the first step of that optimal trajectory. And so this can be shown to be optimal in any sense you want. The drawback of this is that you have a high computational cost during runtime because you need to solve an optimization problem. And what you also need is a mathematical model of your plant, which is not always existing. Or you need to do system identification on your buildings, which again is, lowers the ability to implement them on things like, single family homes where you don't really have the ability to do it at many buildings at once. You can do it for large buildings where, again, large loads, it matters a lot. So you can afford to put money on it, but For smaller homes, you just want quick solutions, quick and dirty, that work without spending too much time on it. And so the last approach, or the last control method that many people have been working on, and also what we'll be using in the future in this talk, RL, or any sort of learning-based control, where you don't necessarily have a model of your building. You gather data, or you have previous sort of like policies that have been gathered, and then you use those, and then you try to optimize those over time rather than ahead of time. And so this has the advantage that you have very low runtime computational cost. It has a disadvantage that you need a lot of data potentially to be able to predict good behavior over time. So if essentially MPC can be optimal from the first implementation that you do it, then RL, will take time, weeks, depending on how you set it up, until it generates similar results. At the end, they perform all very similar, so it doesn't really matter. So the way we get there is kind of like the difference. Okay, so RL, in simple terms, again, it's a trial and error approach. When I say RL, I mean model-free RL. Model-based RL and MPC share a lot of similarities, so I will not talk about those, especially the drawbacks. So when I say RL, I really mean more the idea that it's model-free. I'm also aware of, but I will not touch, there's a lot of work that combines the two. So simple models, learning-based or data-driven, neural network types, physics-constrained neural network type models that don't need the model development. So all of those exist, they're very cool, and they also would be good solutions. We just haven't worked in that area yet. And so that's not what I will be talking about. So I'll talk about these RL approaches. And there's a lot of algorithms, there's a lot of work in these. The stuff I will show you mostly focuses on soft actor critics. Without going too far into detail on what has been done in RL in the buildings, I started talking about it. But I would rather invite you to read this paper that we just put out a month ago. You'll recognize Jan on that also, who is co-chairing this conference or this workshop. So this really consolidates a lot of work in the last 3-4 years, where RL is in terms of energy management for buildings, including how do we get started, what are environments, what are the currently best algorithms, so to speak, what are the big pros and cons, what are the open questions. You can find all of that in there. So I want you to read it and generate more thoughts down the road from there. Okay, so once we decided we're going to go down this road, and in our own development, this is 2018 or so, so 4 years ago, even more, we're like, okay, so this is cool. Let's try use RL. Let's try to use RL for grid interactive buildings. So the next step is, well, how do we do it? So it turns out it's not so easy, because you can't really just go ahead and simulate it. Especially controls for buildings a few years ago was not exactly established. And so, today it's a different problem, but a few years ago, this was not the case. And so we had to go in and take a look. And so some of the models we found were simply too detailed, highly physically accurate simulation models, which are too much to some extent for a control problem. Or at the other end of the spectrum, where when you start aggregating buildings, you just be like, oh, well, let's just take one load for the whole of the US or one region of the US, which is just way too much aggregation in order to be able to study how much we can really flex around. And so this is why we set out, before we started thinking about this problem, we set out to sort of simulator. And this is what I talked about last time, I think at AMLIES, when I came like 3 years ago. And so you can go back and watch that video, so I don't want to go too much into detail on that. But over the years, we developed this into a really nice application that many people can use. People have commented on it. It's been recognized to address some of these SDGs from the UN, which is nice. In general, what it is a very neat GIM interface for many buildings that you can set up the way you want and then study the problem you want to study, even with your own buildings to some extent, although it's may not be super clear, but we're happy to help if you have your own data with that, which we have also done. And so we wanted to have this versatile product, and at the same time provide some benchmark data sets. So whatever you do can be compared on that. Some of the limitations we had in the first version, I'll come to that, or throughout the last 2 years, what people have been using it is that we had pre-computed demand, so you couldn't really shift thermal loads in some sense. You could only do storage shifting, so battery or thermal storage. So the active load control was the main part of the problem that we addressed. But you could very well, because this is how we built it, you could focus on any algorithm you wanted. We did RL, but others have done MPC, for example, and so you can create a really nice benchmarks for any of these and compare them, with each other. Now, everything is obviously open source. You can find it. It's a nicely organized website, and you can extend it however you want it. And we encourage you to do that, because that's how this lives, and integrate new modules or new data sets and new applications, which would be quite interesting. Okay, so now we have this environment, and it seems to be great, right? What can we do with it? Well, a few things, and I'll show you a small example here and then a little bit longer one in a little bit. So the one thing you can do is, obviously, because it is sort of like a benchmark worthy environment, you can start off by addressing some challenges that exist in this field. There are a few that we summarize in this paper. You can read up. One of those, that CA challenge 8, is how well can you train from known previously gathered data. And this is particularly interesting for buildings, because if you go back a little bit, a lot of the RL literature comes from things like robots, or motion planning, or quadcopters flying, and things like that, and highly dynamic systems with many degrees of freedom. Buildings are highly complex, and they also have many degrees of freedom and many degrees of control. However, they're simple in their dynamics. And so, if you have some data that you can pull out the dynamics from, you might be able to leverage and reduce the time that you need to learn the dynamics quite considerably. So that's the part of that challenge that we're interested in. And so what we did is to show that if you do have some simple rule-based controllers for your building, in this case for a battery, you can considerably reduce the data that you need to like a week, rather than, typically when you read RL papers, when people complain about them, like, oh, you need a year worth of data, 2 years worth of data. It's not true. Like, in a week, you can learn exactly and perform as good as the relevant RBC, and then improve it even better. So you will maintain all the boundary conditions you need, all the safety conditions, because you can always fall back to that known RBC. And so that way you can actually eliminate this problem that RL is data intensive from day one. Like, that argument does not necessarily exist, because for any system that you need to control, you can probably come up with some simple rules. Worst case, ASHRAE has guidelines for simple rules for any systems in the building. And that's really one of the takeaway messages, is you really don't need a complex optimizer. You can do simple rules plus a learning algorithm to get what you want. One thing that we've also seen, and was a little bit surprising, is that you can overdo it. If you give if you give it too much data from known logs, it will not perform as well. So just a little bit to get the overall idea is better than providing years and years of data, because in some sense you're biasing it too much into the RBC solution, and then you just off that track. So the balance between how little data you provide and how good you will perform is true. So that's that. One thing that also has been shown in the meantime by another group, which I found quite fascinating, and I mentioned ASHRAE. So ASHRAE has a few really good guidelines of how you can tune your commercial buildings, right? Not residential, which is what I'm talking about here, but for commercial buildings, how you set up your handling units, how you set up your thermostats, and so on. And so the group by Zhang O'Neill in Tamu in Texas A&M, they showed if you do that in simulation, if you do that, MPC and RLC will not have any gain over it. And so for that particular problem, it concluded the same thing, which is if you really spend some time on good rules, you can get very good behavior. Of course, that was in simulation models, so how it's in reality, it's a different point. But again, if you spend the time, so there's no free lunch, right? So what you learn with what you get with the RL is that you can use the time to learn what you're doing. What you get with the MPC is that you have to identify your system, but then you have to use the time to optimize your decision at every time step. And if you have the time to set up good rules, you can also achieve good results. So you can pretty much do anything you want. You just have to decide where you want to spend your time, right? That's kind of like the fun part. You want to spend your time waiting for the controller to learn? Do you want to spend your time for the system to optimize and set up the models? Or do you want to spend your time developing really good rules for your model? So that's really like the decision you make, and there's no trade-off in terms of accuracy to some extent, right? Not for every problem, but at least for these problems here that we tend to see this kind of behavior. So this is quite fascinating if you think about it. Okay, so let me show you a little bit more in depth from this more particular problem of residential demand response or residential energy flexibility that I've been talking about. And the question we were trying to address and we're trying to understand is another one that people have been trying to see is, well, if we need to learn so long, can't we just take learnings from one building and put it in another building, right? So can we learn from one building, take the policy and move it to the other building and see what happens, right? And so you can address it. This is called transfer learning, of course. You can do it in a theoretical sense and, what kind of parameters need to be, or what kind of variables need to be satisfied to be able to do that, or how well can you do it? Can you prove anything on optimality? I'm more interested in what would it do in reality. And so the way we set it up is this just, forward thinking, saying, oh, we will learn for some time and then we deploy it on another building and see what happens. So can we do that? So the short answer is, of course we can, otherwise I wouldn't be talking about it. And so let me show you the paper that also just got published like 2 weeks ago. So you can go ahead and read it or look at it on arXiv, which is not the latest version, but it's the same idea. So what we have set up, and we'll go a little bit more in detail, but here's the overview. We have data from a community in California. It's 17 single-family homes. We collect their data in terms of loads, generation, battery. We know the weather. We know the electricity cost in the area. We have time of use pricing. We know the carbon content. So we can set up all these controls, control for pricing reduction, control for carbon emissions, and so on. So we can set up the environment. We can set up the same buildings in CityLearn. We can evaluate. We'll use the RL controller. We can set up what kind of states are interesting. To be able to learn what we want to do. We can experiment with different reward functions, and all of that is in the paper. I will just show the results. And then essentially what we could do is derive optimal rules for each of these buildings, or can we figure it out in an automated sort of like learning-based way to find these rules. So the buildings are in Fontana, California. They're already built to a really good standard. They're built to high efficiency. They have really good insulation. They have solar panels. They have a home automation system. They have electric heating and cooling. They have battery storage. You can see here. They have all LED lighting. All circuits are monitored, etc. Everything is high efficiency and very much, in line with those first two boxes that I showed, high efficiency and self-generation. And so what we wanted to see is, assuming they all had batteries, which they don't all, but in our simulation, we'll assume they all have batteries. Our task is to control the battery charging and discharging and then see what we want. What we wanted to achieve is reduce the cost, reduce the emissions, because that's what EPRI, the Electric Power Research Institute, has tried to do with this environment, with this neighborhood to demonstrate that. So we wanted to replicate the results and see how much more we can sort of achieve. So let's see what we did. I have three controller comparisons that I want to show you. The first one is the one with sort of like a perfect knowledge, where we just train every building on their own for 12 months, and then we run the controller for 1 year and then show the results in sort of this deterministic way. And that's our results. So every building, we assume at that point, every agent at that point for each building has converged to its best solution, so to speak. But it's optimal or not, we can't tell, but it's the best we can get with the learning-based approach. Then we'll do the transfer learning approach, where we train on one building for 5 months, and then we transfer the policy to every other building, and then continue for the next 7 months. So we have the 12 months period. And so this is a realistic sort of deployment, and see what we can achieve with that. And in the paper, you'll see we did it training from every building, deploying on every other building. So we did all the combinations to see if there is some sort of sensitivity in that, which there wasn't for this particular problem. Okay, so that's that. And then the last controller shown here is the reference RBC, which is what was installed in the buildings for charging and discharging the batteries, which was based on the time of use tariff. And the idea was, you charge when it's cheap, and then you discharge when it's expensive. So the whole idea of, charging in the mornings until 2 or 3 p.m. and then discharging in the afternoon, early evening, 4 to 9 p.m. because it's, twice as expensive. So we did that. This is the reference controller. And then we looked at different KPIs. A first set of KPIs was on individual buildings. So net electricity consumption, electricity cost, carbon emissions, and zero net energy, because that is what we normally do, energy reduction, electricity cost reduction. Zero net energy is not something that's done a lot, especially not on short time scales, only over annually, but wanted to see how we get, how far we would get. And then the other one was, we looked at district level KPIs. So when you aggregate them, and then look at what that is, because that's what the aggregator sees, or that's what the grid operator sees, or utilities see, how these buildings contribute to like the average daily peak in that area, and ramping, and also the peak to average ratio, or the load factor, how that changes with these sort of learning-based controllers. So again, we initialize the controllers with the RBC because we know that already helps, and then we see how much the RL controllers take over and learn. So I'll go through the results. You see the time of use tariff in this chart will be in green. It's the RBC. The perfect knowledge, so like the 12-month sort of optimization or learning process, is in orange. And the transfer learning process is in blue. And then the line here, the baseline, it's the comparison to the no battery. So if you just let the loads have the loads whenever they have, and whenever they happen. So you can see the two that also EPRI was studying, so electricity demand, electricity cost, you see they hover around 1. And so the conclusion from that is, if you're using time of use tariff, it will really not help, and the batteries are not economic. And that is exactly what the EPRI report said. It's no point using them because they're not economic. But if you look at it from the more optimality or learning-based perspective, you see that there's quite a bit of possibility to reduce both the load, and with that, the cost, 20% less cost, in some sense, 15 to 20%, as opposed to increased electricity demand. So this is quite impactful, I would say. So it shows you that there is energy demand flexibility in individual homes. You just have to unlock it, and time of use is not necessarily the best way to do that. You can continue carbon emissions. This is also something that you may see when you look into battery storage or battery control work or research, is the conclusion that using a time of use tariff will actually increase your emissions, because that's just how it happens. Whereas if you control for it, you can reduce them. So reduce demand, reduce costs, reduce emissions. This is all towards a more sustainable behavior without knowing anything about these buildings, I may add. And some of these, the blue ones, are by learning from another building and deploying on, another building. So these are all the average cost, or the average KPIs for the whole neighborhood aggregated. So this is pretty cool. Again, because we don't know anything about these buildings in terms of, who lives in there and so on. Zero net energy. This is the monthly, I think a monthly net load profile is tough for everyone. So far, that just shows that there's not enough renewable in the grid to be completely zero net at all times. The goal should be, minute by minute matching, I guess, at least hour by hour. Daily peak, again, quite a difference. If using time of use tariffs, your peaks actually might increase just because everybody's doing the same thing at the same time. So it's not really a good idea to do the same tariff for everyone. Whereas if you're learning, you can actually avoid that. Ramping is the worst. That is because everybody's doing the same thing at the same time, and so you increase the load. You may be able to coordinate this a little bit, especially if you're using time of use tariff. But if you just let it free, it will end up in a disaster in that sense. And then the peak to average ratio, we didn't see much change. I will add, I forgot to mention, so we're not coordinating anything here between the buildings. These buildings are all sort of like their own, on their own. They don't know about the other buildings. They don't know, when the others are using loads, using energy or not. And so that's what I was trying to hint at. If you wanted to improve these bad numbers for time of use, you may have to do individualized time of use, for example, to try to coordinate a little bit between them, or just generally try to see how much further you can push this by trying to coordinate the loads as well. The other thing that I haven't mentioned that often comes up at this point is, how about thermal comfort? The people are, do you do anything about that? And so the short answer to that is, we haven't even started looking into this. All we do here is load matching. So we actually have the actual load profile for the homes. And so we make the assumption that if we match the load, whether from the grid or from the renewable on site, it is what the occupants would want. So if it is thermal comfort, if they're comfortable, then we assume that this would already imply that. Certainly didn't make anything different from how it was in those buildings. So that's kind of like a conclusion from here. So I think that's a pretty good show. And so this shows that there is, more that we can learn more and we can continue more. And so if you look a little bit more into detail, here are the individual loads. The color scheme changed, but bear with me. So black is the actual loads of the building, the smart meter data. Red is if you do the time of use control, so that you can see here the net loads increasing in the morning when you charging a battery, and then discharging at night, so your net load goes down. And then red is the one where you have the RL controls. You see there's no high spikes. It's kind of like continuous throughout the day. So it's hard to see it this way, but these are the individual loads. What you can do is you can aggregate these, and of course everybody's batteries discharging and charging at the same time. So you get the good stuff here, you reduce the peak quite a bit, but you also get the bad stuff here. And in this particular case, your peak actually increased, which is not a good thing. So again, some sort of coordination or some sort of limiting how much load you can pull, how much energy you can pull is necessary. Otherwise, this is worse because now you have a higher load in the middle in terms of what you're pulling from the grid. So again, and then the green, right? The green is like almost rather continuous, relatively small. And if you compare that to the initial curve that I showed you here in blue, it's we're getting there. We have your low profile during the night, and then kind of like a little bit of a up and down and up during the day, and then again a little bit smooth over the day. So overall, this is kind of cool because again, we didn't really have to know anything about the buildings, but we gave it the right signals on cost and emissions, and so this is what came out. What is interesting, and if I go back, one thing I forgot to mention, if you look at the black curves, they're all kind of different, right? If you look at this number 1 here, it's like straight down, up. If you look at number 10 here, it's like down, up, really down, and up a little bit. If you look at number 4, it's like slowly going down and then up again. And so what this shows is that every building is different, but which we already know, but the learning controllers can take advantage of that difference. And the learning controllers, by taking advantage of that difference, can unlock this flexibility that we're needing. So basically, the reason we can flex in this case is because everybody's different. And so that's kind of like a cool realization, right? We all are different. If you aggregate too many, then that might, cancel out. But if you look at it at a feeder scale or like, whatever close by, it might be just enough to not have to increase infrastructure at that point. The other thing, and that was kind of like for my hint, what I was hinting at is that, this kind of behavior, some people call virtual power plants, you can dispatch energy as you need. People started to understand that you can tally those up against transmission cost and new sort of like grid cost. And so in this case, this report, again, like just a month old, I think, compares the cost of generating a new thermal or procuring a new thermal power plant that's driven by gas, grid scale storage, and virtual power plants, which I'm not sure if it's residential in this case or just many, many loads. And so you can see the win is not necessarily, or the comparison, that the virtual power plant actually is cheaper than all the other costs. And the advantage is not necessarily in the energy, so not in the green part here, but because you can avoid building distribution, transmission, right? And also reduce the emissions along the same time. So that's kind of like a different way of looking at it. So this will come more and more. And so unlocking this flexibility is kind of like, I think, our next grand challenge in the next 5 years, to do that at scale with every sort of demand provider or net demand generator. So whether it's individual homes, whether it's schools, whether it's office buildings, the better we can unlock this, the more easier we can integrate a lot of renewables into a grid and, transition into a clean grid with, secure energy that's available to everyone. So that's really something to keep in mind on. Okay, so a few words of what's next. I have about 10 more slides, I think, for those of you who keep track. Yeah, 15. So what's next? Okay, so we got CityLearn. That's shown here. Well, we also, over the past 2 or 3 years, DOE had a lot of projects generating building energy models for the US that are more specific. And so one of them is this end-use load profile database, where if you go in, you can literally pull, OSM models, Open Studio models, and Energy Plus models on like a typical building anywhere in the US. You will get the model with its typical setup and the Energy Plus model. So if I wanted a 1,500 square foot building or home in California, I can go in there and get the typical example for that. If you wanted a 1,200 square foot home in Tennessee, then I can go in and grab that, and I get the different vintages and so on. Of course, if you have a database like that, you can simulate almost every building in the US or every residential home, which is pretty cool. But you can also start augmenting it with set points from other data sources, like ecobee has their own database with set points for thermostats. Obviously, you can integrate weather. So at some point we thought, well, wouldn't it be interesting if you could just take this massive resource that's available and that's very typical US building stock, and then here we have CityLearn that we can do all these cool things like having energy flexibility. So again, we just link these together. And so basically over the past 2 years, this is what we did. And so because we had these colleagues in Italy who figured out a way to generate nice, LSTM models based off Energy Plus fractional load simulations, you can now take this Energy Plus simulation models that we have that represent the US building stock, generate the dynamic models for them. And so now you can control partial load, and so you can move thermostat, you can create thermostat control, and with that occupant behavior into CityLearn. And so that's pretty cool, because now again we can understand the flexibility that's available in all of America's buildings, and that's really powerful for the for the future. And so again, like I said, a lot of contributors over the past 1.5 or 2 years that happened. And so we'll highlight a few names here. Giacomo Buschimi from Politecnico di Torino, who worked on these LSTM models, Catherine Casper from Concordia, who worked a lot on occupant behavior models, and then Kingsley and Wei, who is my student, and he, spearheaded the whole thing and organized it and make sure that the code is useful. So really, really a lot of cool stuff that happened. And so we're really proud to release this like a month ago or so, or two weeks ago. And so you can go in and check it out now. We call it beta, but it's pretty cool, in pretty good shape. So again, we can do now load shedding, which we were not able to do, but now you could, preheat buildings, pre-cool buildings, just switch thermostats off. So more classic demand response, what also CalFlex does, and just turn your thermostat up when it gets too hot or too cold in the for the grid. We also generated a new data set in 3 different climate zones. It's not released yet because we're writing the paper, but soon it will be released. Let us know if you're interested in that. And we're not done. Like I said, this is all public, so it's free to use and it's also free to extend. And so again, we're integrating occupant behavior models. So how do people react to demand response? How do they overwrite? What are the different personas you can integrate in these so you can have some realistic behavior? That's one very interesting topic. Of course, EVs, super interesting. We haven't done it specifically yet. There is a group in Portugal who's actively working on this now and integrating it, so that maybe in the next 3 to 5 months will be out. EVs, of course, functionally, it's the same thing as a battery, but there is some, things that need to go in the background, like how far do you discharge during the day and so on, and when you come back, and there are some boundary conditions that need to be fulfilled. But in practice, is something that will be coming up more and more. So that's pretty cool. And with that, now you see you can go from individual occupant behavior and presence and things like comfort, preferences, all the way of how that integrates and aggregates over like a whole neighborhood and even larger. And so that kind of like hints at this, everything's connected, because you can kind of see that maybe this energy flexibility we're looking for is already there. We just haven't really been able to really quantify it and really understand it in this detail. And so this is where our work kind of like tries to, poke in, and then hopefully it can unlock some further thoughts down the road. Yeah, you can do it pretty quickly in 12 lines if you want. And get started. It's written really so that everybody else can use it. That was always our ambition, so feel free to check it out. Many papers have been written over the past 1.5 years or so in this, comparisons, some more buildings focused, like the kind of work that I showed you, some more computing focused, like look up here, meta learning, or just about offline reinforcement budget, and like how far do you need to compute and things like that. So very, very exciting. We're also doing this crowdsourcing stuff where we do a challenge every year. So this year will be the 4th year. This was last year. You can check out on YouTube our the winners and the whole thing. And this year, stay tuned. Like in a few weeks, I will announce a new competition, and you can again compete and win some prizes. It's going to be exciting. If you want to learn, we have, like I said, it is written, so it's easy to use, but also we have, events where we participate at the Climate Change AI Summer School that's about to start. And then later this year at BuildSys, we'll have a tutorial on this during our LAM and also at the BIPSA. And then our LAM is also one of our workshops that we organized the last 3 or 4 years, where we gather, folks in this topic. We use a lot of RL, but obviously open to other ideas, other ideas, generally in how we can use AI in energy management for buildings and cities, and generally in smart and sustainable infrastructure. So with that, I'll end my presentation. The key takeaways on the technical side is that you can really jumpstart, if you have learning controllers, jumpstarting with known simple rules works really, really well. If you are not taking care of your loads, then you can have unintended consequences. So these peaks that accumulate on times that you don't expect them, just because everybody's doing time of use control. That is something that needs to be taken care of, because otherwise we cannot unlock this, you know, energy flexibility that we're looking for. And then, as I kept saying, you know, if you're interested in checking it out, working on it, testing things out, you can look at it on GitHub, or also just get in touch. You know, hopefully you enjoy it. So with that, thank you very much. I can take a few questions. Feel free to get in touch however you wish. Thank you.